is equal to sine x. All right, so I know what f of x equals sine x looks like, and I'm going to draw, well, the first period of f of x equals sine x goes from 0 to 2 pi. And I'm also going to continue this one period to the left. So we have negative 2 pi, negative pi, 0, pi, and positive 2 pi. And the graph continues on from there. Some other markings I might put in here are pi over 2 and 3 pi over 2, as well as negative pi over 2 and negative 3 pi over 2. And along the y-axis, I've got y is equal to positive 1 and y is equal to negative 1. All right. So now we'd like to draw a picture of our derivative function. Now, y equals sine of x is nice and smooth. There's no sharp corners, no breaks, or anything like that. So y equals sine x is a differentiable function for every value of x. And so our derivative should exist everywhere. We shouldn't have any holes or gaps in our derivative. Okay, so if I'm looking at this picture, some things that I might acknowledge are places where I have flat spots on my original function. And so I've got a flat spot at x is equal to pi over 2. So that means that will be a 0 on my derivative function. I also have a flat spot at 3 pi over 2. So that tells me that I have a 0 on my derivative function at 3 pi over 2. Similarly, I've got a flat spot at x is equal to negative pi over 2. Tells me that I have a 0 on my derivative function at negative pi over 2, as well as at negative 3 pi over 2. All right. So looking at our picture, I'm going to look at the first gap, or not the very last branch, I'll deal with those last, but the first space between walls, negative 3 pi over 2 up to pi over 2. Our original function sine x is decreasing, moving downhill, tells us that f prime will be below the x-axis. Now, how far below the x-axis? Well, as I look at this hill that I'm sledding down, the best part of the hill, the steepest part of the hill, is occurring right about here at negative pi. So that should be the place where my derivative function is farthest away from the x-axis. All right, let's look at the next portion. From negative pi over 2 up to positive pi over 2. Our original function f is increasing, has a positive slope, tells us f prime should be above the x-axis. The steepest place in this interval is when x is equal to 0. So on our derivative graph, that is where the derivative should be as far away from the x-axis as possible. All right, so our next section over, from pi over 2 up to 3 pi over 2, f is moving downhill, decreasing. So f prime is below the x-axis. F prime is negative. And our steepest place occurs when x is equal to pi. So that is where f prime is farthest away from the x-axis. Now, our last increment here, I mean, realistically, the sine function continues. So at 2 pi, we know that our function is going to continue. And so the steepest portion is right at 2 pi. So that's where our derivative should be as far away from the x-axis as possible. And similarly over here, if we extended our sine graph past negative 2 pi over here on the left, we would see that the steepest place is right at negative 2 pi. So our derivative graph should be as far away from the x-axis as possible when x is equal to negative 2 pi. And so here we've got a picture of the derivative of sine x. Anybody recognize this picture? Yeah, this guy is cosine. So when f of x is equal to sine x, the derivative function is cosine x. So the derivative of sine is cosine. So let's say that we started out with the function f equals cosine x. Starting with this one, try drawing the derivative and see what happens. See if you get back the sine x graph.
Sure.
You get the mirrored across what? I mean, like mirrored across the x-axis?
Yeah.
Okay. Yeah, so I think if you take the derivative of this graph, of the cosine graph, you're going to get something that looks like this, only reflected across the x-axis. And so double check that, but you should get something like that. Yes?
Are they the same as far as y value?
That's a really good question, and based on our sketch here, there's really no way to tell that, but it does turn out that yes, they are the same in terms of the y values.
If you take the derivative of cosine x, that would be like we are taking derivative of sine x twice.
That's correct.
So that's going to completely change it.
So that is going to be your derivative. So if I start out with a function g of x is equal to cosine x, and I take its derivative, well, that's our derivative of cosine, but it's also what we would call a second derivative of sine x. So we can take the derivative of sine x. And we'll talk more about second derivatives and third derivatives and 150.
Go back to sine by taking derivative. Because we're taking derivative of sine twice. That would be
That's right, we're taking derivative of sine twice. Yep. Okay, so let me give you some practice problems before you head out.